And it's a pleasure to be there. I'm sorry I'm not there in person. Another talk yesterday kept me local. And on the other hand, as you heard, I spent quite a bit of time at Iowa State. And let me tell you, anybody who spends a lot of time at Iowa State is pretty much afraid of Nebraska. So I'm afraid if I came to Lincoln, I'd be worried about cornhuskers around each lamppost and being tackled and once more humiliated, as often happened on the football field. So anyway, I feel safe at this distance and am happy to be here at least this way. If my slides are up, you see that the title slide is Big Data in Context. That's because I intend to say a little bit about a broader context before I do a dive into data per se. I believe my colleague Fen Zhao from NSF has already given you part of a view of our big data initiative, and I know some other colleagues will do as well. Let me proceed with the next sentence, which is my caveat auditor speech. Please be advised that the opinions expressed in this talk are mine, not those of the U.S. government. I'll try to distinguish between what I think are facts and what I think are my opinions, but I do liberally salt opinions throughout my my talks. What am I going to talk about? Well, outline. I'm going to say a few words in general about what I call the entrepreneurial state. NITRD, the Networking and IT R&D program run out of the White House, is an example of the entrepreneurial state activities. I'll focus in on general comments on big data and then end up with a few comments about NITRD and big data activities. So without further ado, you might want to read a very interesting book by Mazzucato, who's a British economist, with the title Entrepreneurial State. We talk about the government getting out of the way of innovation. I'd like to point out that at least within IT, the government is responsible for much innovation. Mazzucato quotes this interesting statement in her book that since the founding of the U.S., we've always been torn between two traditions, the activist policies of Hamilton and Jefferson's maxim that the government that governs least governs best. But with time and usual American pragmatism, this rivalry has been resolved by putting the Jeffersonians in charge of the rhetoric and the Hamiltonians in charge of the policy. That is, the government still does an awful lot of good things in terms of innovation, and nowhere is that more in evidence than in IT. And we can look back 150 years. In the 1940s, it was the U.S. government that supported Morse's development of the telegraph. The private sector refused to invest because it was too risky until the risk had been abated by constructing of a actual telegraph line between Baltimore and the U.S. under federal support, and that was a good example. Then the federal or the private sector bought in once the risk was reduced. In the 1890s, a guy named Herman Hollerith, who had been an engineer at the Census Bureau, developed punch card data processing for use in the 1890 census, cutting the time from 15 years anticipated processing to 4 years processing to take care of that data processing. By the way, Hollerith's work developed into a company you probably heard of called IBM Corporation. In the 40s, Mauchly and Eckert received substantial Army support to develop the electronic digital computer, the ENIAC, which was used, projected to be used for ballistic table speed-up calculations. It wasn't finished till just after the war, but then turned out to be very useful in nuclear calculations one place or another, and of course the rest is history. The computer has turned out to be important. In 1965, almost 50 years ago now, program officers at DARPA, Larry Roberts and Bob Kahn and Vint Cerf, in turn invented something which we now call the Internet. Also done under significant federal support, first from DARPA and then from the National Science Foundation after that. So we have a proud tradition in the United States government of supporting the development, the innovation of IT. Now, of course, well, and not to disparage the private sector, this is a busy slide, and you can certainly have these slides and look at them later. This is an example of continuing innovation in information technology. It shows recent times since the creation of the internet and shows the interplay between private sector R&D and university R&D. Bear in mind that university R&D is usually federally sponsored university-based R&D. And you'll see that many times the university red lines precede private sector investment. The green lines show products, and then the fat green lines show when the products are a part of a billion-dollar industry. And so it's been the wonderful interplay between the private sector and the public sector that has created remarkable advances over the last 50 or, if you like, 150 years in information technology. One last general comment. Perhaps you've read Clayton Christensen's series of books on disruptive technologies. The first book, where he introduced the terminology, was in The Innovator's Dilemma, published in the 90s, where he introduced the distinction between sustaining innovation and disruptive innovation. Incumbent firms, of course, want to practice sustaining innovation, where they can make their current products better, and their customers want their current products made better. So, for example, in the 80s, incumbent firms tried to produce better mainframes and better proprietary networks. It was startup firms and the government that can engage in disruptive innovation, creating PCs in garages and creating the internet under federal support. My guess is it will always be the case that disruptive technologies will be created by either startup firms or government support where appropriate. And we can count on the established private sector to continue to work very diligently on sustaining innovations, making current products better. I leave you with one question at this point before we dive deeper into specific subjects. Is big data an example of a sustaining innovation or a disruptive innovation? Or in what sense is it sustaining and in what sense is it disruptive? Then you can decide who will probably be the prime players as we go forward. Now let's talk about our NITRD activity, which has been in existence since the HPC Act of 1991, by the way. I've had the great pleasure of being associated with the activity since 1995, when I represented NSF on the large-scale networking coordination group of the NITRD activity, and we received considerable additional federal funding for the next generation internet, which, by the way, resulted in the construction of Internet 2, which I'm sure you're familiar with at Nebraska. In the last decade, our activities have assisted in a considerable plus-up in federal investment in IT security and information assurance. Now, the topic of today, we've already, I believe, contributed to a general focus on big data, which has resulted in more research monies, investments available for big data. I'll call to your attention as a forward-looking that more recently we've gotten quite involved in cyber-physical systems, which is closely related to another phrase I'm sure you've heard called the Internet of Things. Internet of Things may be the technology that underlies cyber-physical systems, which are the applications developed on top of it. Even more recently, we've begun quite a bit interagency upsurge in investigation of how to do privacy research and development. So these are areas that are coming. Big data is certainly already here. Just a few more words about NITRD, because we're sort of a program. You know your funding agencies, but you don't necessarily have reason to know the interagency NITRD program. For one reason, we camouflage our existence by changing our name every few years. Started out as the HPC group, then the HPCC, where we added networking to the computing. CIC in the late 90s became our name, then IT R&D in the early aughts, and then we finally added an N, so we're NITRD now. But since it's been a while since we haven't changed our name, it's probably time to change our name again to help confuse the public. What are we? Well, NITRD is an interagency program to enhance coordination and collaboration of the IT research that's performed and supported by federal agencies. The National Coordination Office, of which I am the director, provides the support for the NITRD program. We report to OSTP in the White House. We interface for NITRD with OMB, with GAO, with Congress, or anybody else who may want to may want to interface with us, but bear in mind that it remains the agencies that are the source of the actual research and development itself. Our idea is, our station in life is to help coordinate that activity, not support or perform that research ourselves. Our members, this may be too small to read, but we have 20 federal agencies who are members. Reads like a who's who of federal agencies in DC. Almost all of the support for IT research at the federal government level is represented by members of the NITRD organization. As an example, at the top I say Department of Commerce too. Well, Commerce is a big department. Two of its bureaus, NIST and NOAA, are members of the NITRD organization. We have 5 similar members from the Department of Defense, from DARPA to the Office of the Secretary of Defense to the service agencies to NSA, so forth. 3 bureaus of the Department of Energy, 3 from the HHS, and so on and down the line. Then you see some of the independent agencies represented who show up directly. We have 8 program component areas. This means areas in which we divide our budgetary reporting to Congress, from cybersecurity to supercomputing to high confidence software to information management to networking to socioeconomic implications to software development and productivity. We have something like 14 or 15 coordination groups that fit within these categories of program component areas. The most recently established ones we call senior steering groups. Big data is the one we're here to talk about, which fits in our HCI-IM program component area. Cyber physical systems fits in the high confidence area. Cybersecurity and privacy fit in the CSIA group. We have a cross-cutting area that Congress asked us to get into called health IT, but the health IT investments are reflected in the various other areas of which are sub areas of IT research and development. Wireless spectrum efficiency is a new area supplementing our long-term activities of internet activity. So an eye chart for you that you can look at your leisure shows that the agencies submit to OMB and then to Congress about $4 billion of investments in IT R&D, the number at the bottom right of this table. And then each row represents an agency's contribution. NSF is more than $1 billion per year of investment in IT R&D, on down to smaller agencies, smaller participating agencies. And then the column headings show the various categories. You'll note that HCI-IM, sort of in the middle, has $814 million per year in $1 million year investment. That's the second largest category, so we're already heavily investing in information management and related activities. Well, all right, now let's start focusing a little more on data. I bet that you know that last year 2 important documents were submitted, announced by the government, where open access to U.S. government data becomes the default. You have to apply to keep your data private rather than apply to make it public. Even more germane is the document which it mandates public access to federally funded science results, where science results not only includes journal articles supported by research supported by the government, but also the science data. This is required now of all agencies who fund more than $100 million per year of research. These 2 sources of open data are going to contribute to available big data for processing in manners to be determined by the big data activities that we're just to talk about. But I want to also call your attention to something that was just signed into law last spring, called the Digital Accountability and Transparency Act, and you'll note that that's a clever acronym that spells DATA. So it's the Data Act of 2014. It's a law that aims to make information on federal expenditures more easily accessible and transparent. Moreover, they actually imply that controlled vocabularies and ontologies should be involved to make accessibility and transparency interoperability. Wouldn't that be nice? Now, it turns out it's the Department of Treasury that is directed by the Data Act to work with the agencies to do this for all of the agency information. By the way, that includes grants and contracts as well as normal federal expenditures. So if this can actually be put into practice, all of the information that NSF and the other agencies all the support that they provide to universities and others for research and development will become much more available for scrutiny and analysis than it has been in the past. My opinion is this is a wonderful thing to do, and it won't be done in a year. This will take more like a decade than a year to do, but that will depend, even that will depend on the participation of people like you all who help us figure out exactly how to do it, how to develop the big data processing capabilities that will put teeth into these great ideas. Speaking of big data, let's get down to business. You probably have heard more times than you wish that big data is defined by a bunch of V's. I think we've come up with about 17 V's now that we can use to describe big data, but the original 3 were volume, velocity, and variety, where the size, the rate of acquisition, or the complexity of the data is beyond our ability to use commonly used software tools to capture, manage, and process it within a reasonable amount of time. That is to say, we can store more than we can profitably process. We've got to find ways to have the processing catch up with the storage capabilities. Well, why are we concerned with that now as opposed to 10 years ago or opposed to 10 years in the future? Certainly the major reason in my mind is big data, as we understand it, is a child of the internet. One of the wonderful developments of IT that is created by the 25-year-old or 50-year-old, depending on how you measure it, development of the ARPANET, the NSFNet, and the internet, because it has successfully connected the islands of information surrounding individual computers into a continent of information where increasingly almost all computerized information is accessible over the internet. Well, note I said accessible. I didn't say interoperable. I believe one of the major challenges in front of us for big data is how do we turn non-interoperable data on this continent of information into interoperable information. That's where we move from a mess of data to a cornucopia of data, which will do increasingly good things for us. We've been aided along this line by Moore's laws, not only for CPUs, but for disks and sensors and networks. You know as well as I the wonderful increases in performance along all these dimensions that occur on a decade-by-decade basis. Disks is a good example, since that's where we store this stuff. Has gone from $1 a byte back in the 50s when it was introduced to $1 for 10 gigabytes today. I suppose $1 per terabyte will show up in the near future. In fact, one person defined the era of big data when it became cheaper to save stuff than to throw it away. You can add more disks efficiently enough just to keep the old stuff that you had, not that you can necessarily find it again, but if you don't throw it away, it's cheaper to keep it and just add more disk. That may be one way to characterize the big data era. Sensors are another example, remote sensing, cheap remote sensing, video surveillance, environmental sensing, scientific instruments. All of these are contributing and laying the basis for the Internet of Things, which is about to be much bigger than the Internet of People, right? There's only 7 billion people. Probably we will all live to see 7 trillion devices connected to the network. I'm told that this is the very year where there are more devices connected wirelessly to the internet than there are people in the world. So already there are more than 7.2 billion wireless devices of one sort or another connected to the internet. That will go up by orders of magnitude over the next decade, I believe, contributing both to cyber physical systems activity and the urgent need to learn how to process that data with big data applications. Saying a little bit about volume, variety, and velocity, big data, I'm sure you understand, requires big computing. You don't do big data on your PC. Supercomputers, of course, are thousands, soon to be millions of PCs strategically coupled together. Well, you're going to need something like that, or at least you're going to need server farms with thousands or perhaps millions of servers loosely coupled together to process data, if you want to call it big data by traditional definitions. Or maybe you can reduce yourself to a cluster, but anytime you're thinking about a single PC, I don't think you're thinking about big data. You're thinking about modest-sized data. Although I should point out that some investigators have started redefining big data to mean we're dealing with all the data as opposed to a statistically significant subset of the data, which, by the way, will require the statisticians, are requiring the statisticians to reinvent their discipline, putting more emphasis on whole data set processing rather than statistical subset calculations. Now, big data turns out to require new database architectures. The old standby relational database architecture, which was announced in 1970 and by 1980 was becoming a workhorse and is still a workhorse, doesn't seem to scale to the volumes that we're talking about already. So new databases under the acronym NoSQL has found ways to limit functionality and therefore do scale to bigger elements. NoSQL, by the way, I'm told stands for not only SQL. It doesn't mean don't ever use SQL, because for reasonable size databases where you want the additional functionality, SQL will remain a workhorse. But it's been augmented by big table and document and column-oriented databases, and a new phrase that's entered the public parlance within the last couple of years, graph databases. Now, computerists and mathematicians have talked about graphs forever, hundreds of years, and graph databases have been a specialist terminology for decades. But I believe the word graph database is coming into popular use, and that I'm going to say more about that in a minute, because I think that is a dimension of big data that's going to be increasingly important. Saying first about velocity, we've had some successes there again with highly parallel systems for online transaction processing, such as Google search and Amazon ordering. Millions of orders and millions of searches can be performed concurrently if you have enough computers that are doing it, and if your software is smart enough to create systems like Hadoop, or the as Google originally called it MapReduce. This was a good example of a major development in big data software that, by the way, was a product of the private sector, not a product of public sector support. So again, we have a question in my mind: is big data an sustaining innovation, or is it a disruptive innovation? And that relates to how will the interplay between public and private sector occur as we go forward. Probably another dimension which has shown itself in certain places is smart sensors. The Large Hadron Collider at CERN generates a petabyte of data a second, which is quite a bit of data, but it only has to save a petabyte a month. That is, it is a smart enough, the LHC is just a computer with fancy I/O devices attached to it, called particle accelerators, and it can figure out for itself whether there's something potentially interesting in a given picture, and then save it, and then saves a petabyte a month for further processing in every physics workstation around the world. Well, if you have a good model like the physicists do, you can do that. If you don't have a good model of the data that you're saving, maybe you have to save it all. Well, people have now started talking about microclouds. Maybe every sensor, every environmental sensor out there will be a computer with a significant amount of memory, so that the data it collects can be stored locally rather than sent down the fire hose when there are trillions of them further to the processing. This brings us back to the idea of PIM, processor in memory. Maybe the microcloud becomes the place where the data is stored, and then you send instructions out to the processor associated with that sensor, and only have to send down a small amount out of data, like the LHC currently shows us. I believe that variety, the diverse big data, is where some of the greatest challenges exist. My preferred phrase for the biggest challenge is the interoperability of heterogeneous data. Some people, anybody would call it a major challenge. I think I would call it the major big data challenge, because you can't do it until you really figure out how to do the metadata right, which probably means semantics, which probably means ontologies, which are words that aren't well enough understood, even in the research community, to be able to have launched a major development in this area. Other people will talk about the long tail of many inoperable science data sets and how can we get them together. Well, clearly, metadata of some sort is going to be required to enable interoperability between those areas. We have one sterling example, and which I'm proud to say comes out of the U.S. government, called semantic midline, that I'd just like to highlight as an example. This relates to textual data rather than tabular data, which, by the way, is often viewed as the harder job. Unstructured data is harder to process. Text data is harder to process than tabular information. Well, this is tackling the harder job and making some pretty good headway. NLM, National Library of Medicine, has for years maintained a database called Medline, which is a database of the titles and abstracts of 22 million biomed research articles. Their goal is to have every research article in biomed in that database. Semantic Medline has created a knowledge base out of that information base by using semantic, I'll say semantic web technologies, but they're actually technology neutral and can use other types of semantic forms as well. You find the key sentences in each of the abstracts, and they find about 3 key sentences describing what is proven in the in that article, and that's the key sentences are found by linguistic analysis, natural language processing, which is a major contribution by Tom Reinflesch and his colleagues at NLM. They utilize the Universal Medical Language System, UMLS, to solve the synonym problem, and then can use IT-developed systems like the semantic web or other similar systems to put all that information into a form. 66 million triples, RDF triples, or key sentences, are found and are connected together in a connected knowledge base, which is so good it not only really directs investigators to information they should read, not finding a million hits as a Google search, but showing you the most relevant articles. But this is so good that it also can connect the dots itself and create new scientific information out of connecting factoids that are in separate articles that no one person had read together. They are getting articles published, scientific discovery then, articles published based on connecting the dots mechanically through semantic midline. I believe that this is a major new element of scientific methodology that over the next decade or two will augment the current methods of scientific discovery. Extremely important and a major part of big data. We got started several years ago with an interagency initiative. We focused on core technologies, domain research areas, emphasis in science, since that's our business, focused on challenges and competitions, and of course raised the question about workforce development, which is now a major concern. Within the core technologies, we initially focused on asking for research in collection, storage, management, visualization of big data. Data analytics is a popular term. Data sharing and collaboration is important. You not only have to have the big data, you have to make it accessible to many different participating communities. Scientific research data is a wonderful cornucopia of opportunities. Astronomy has made wonderful progress because of semantics in their virtual observatory. Data.gov is where the data, federal government data, is being placed, where we still just barely getting started on semantics. Earth observation systems, the government has 250 or more Earth observation products strung across 12 to 15 agencies right now. You can imagine that at the moment, not many of those systems are very interoperable. The biologists have been in a leadership position. The genomic database has given us the human genome. Proteomics are similar wonderful step forward, again, because of collaboration and proper organization of the data. The materials people are attempting to simulate or emulate the genomic systems by having a materials genome where we can do in silico what they've had to do in the laboratory for determining materials characteristics. Nanoscience and technology, which overlaps materials but at a nanoscience level, is making good progress. NSF has some general data projects such as Data1 and DataNet. I've already talked about big data and at the particle physics at LHC. Challenges and competitions are meant to engage a broader public as well as card-carrying researchers. Workforce development, I should say a special word to you all, since we're trying to figure out, you are trying to figure out, is data science and our data science degrees something different from computer science? Is it part of data science? Is it part of statistics? I think the cutest definition I've heard is a data scientist is a computer person who knows more statistics than his or her colleagues, or a statistician that knows more computing than his or her colleagues. In other words, it may be that an incipient area called data science will be an amalgam of what we currently understand as aspects of computing and aspects of statistics. I'll stay tuned while you all decide what it will be and develop that for us as we go forward. A wonderful table that appeared in a recent book on big data is an eye chart that, again, you might want to look at, talking about data from yesterday to today to tomorrow. And if you look at this in terms of these various categories and timelines, it gives a pretty good idea of where we may be going and where we want to go in terms of future research and development to carry the era of data into the best possible way to aid society in coming times. Well, what about coming times? What are we doing? Next steps. Well, actually, the most recent step, the Board for Research, Data, and Information of the National Academies had a big data day a week ago, and you can find all of the talks and the slides, I think, both on a National Academies data set and on our data set, on our NIDARD data set as referenced there. Very interesting comments from federal agencies and from university and private sector observers who are helping us figure out which way we go. We have a big data RFI on the street. I think Fen probably talked to you about that recently. The comments are due real soon now. And these are to look at what we are proposing to do and let us know whether you think we've left anything out or have expressed things in an improper manner. We would appreciate any feedback you can give us. After we've processed the return information from the RFI, we anticipate holding a public workshop somewhere in early 2015 where we would review those results, ask for additional public input, and then go into our smoke-filled room, lock the door, and by later in the year have a puff of white smoke come out the chimney and announce an interagency strategic plan for big data R&D. In the past, these types of big data these types of interagency strategic plans have been useful for instilling confidence in both OMB and Congress that the agencies are ready to make good use of additional resources to be invested in important areas. We can hope that that will transpire in this case as well. I'm at the end. I have two more slides. Informatics writ large. I'm thinking that we are at the very early stages of having a science of information to underlie the technology of information that we've now been working on for the last 50 years. Some physicists are saying information is physical, not ephemeral, that it's part of physics. Some physicists have even come up with the cute phrases, it's from bits. That is, we can't even talk about things without talking about the information that we get that allows us to deduce that things must be there. Maybe we're seeing a replay where in the 19th century the technology of the steam engine led to the science of thermodynamics and an understanding of energy in general. maybe now we're seeing a science of information begin to emerge from the technology of information that we've been working so diligently on, at least since the invention of the computer. If that happens, just as thermodynamics led to applications of energy that were undreamed of in steam engine days, I suspect that a science of information will help us dream up new information technologies later in this century that, again, it would be pretty hard for us to imagine right now. However, the IT future is interesting enough even before the science kicks in. Data-intensive science appears to be revolutionary science that will give us new ways of coming up, new methods to come up to scientific results that will accelerate the development of science. Data analytics and other big data services are clearly of major opportunities for business and government as well as science, so this is a multi-sector activity. Furthermore, big data has already been the basis for significant services to the public, like the web, Google, and Facebook, and challenges for things like privacy. I suspect that as we enter the big data era further, we will have new services that will be as interesting to the public as the web, Google, and Facebook have been in the past. In any event, we're entering a bright future, and big data is right at the center of that future. So I encourage you to turn as much of your attention as you can forward to this area and help us pursue wherever the future of big data may take us. Thank you very much.